Gallimine research team from Pingry.
So first off, why are we studying neural networks? So neural networks are used in almost all kinds of machine learning tasks, from classification, image classification, image detection, or in things like self-driving cars. Neural networks play a major role, and so we are trying to understand how the individual parts of the neural network work and how structure affects the neural network, so we can better deploy them in a actual machine learning setting. And so by understanding the structure, we hope to get better insight into what goes on inside a neural network specifically, rather than just seeing it as a black box that can just take in inputs and throw out an output.
Yeah, and the really important thing here is just that structure in general has not been studied extensively so far, so that's what we're kind of hoping to change.
So our project is examining neural nets. A neural net is basically a computer system modeled after the brain and nervous system. So on the top right, there's a diagram of a node which represents a neuron, and neural nets are made up of a collection of these nodes, just like how the brain has neurons. So the node has multiple inputs, and basically the inputs are summed, and through an activation function, which will compress the values into a range from usually like 1 to 0 for easier use. So below is a diagram of a neural net that classifies points, either orange or blue points, and the axes are what's being inputted. So you can see x1 and x2 in the input layer. And then in between is just a hidden layer with 3 nodes. So all the information is fed from the previous layer, and then it goes through the hidden layer, and then that information is summed together, and then it's into the output layer, which will classify the point as either orange or blue.
So, as Katherine said, we're basically trying to find a boundary between the points of two different classes, and as we find this boundary, we have to keep in mind this concept of overfitting. And so, basically, as you can tell by the middle image, that's the ideal boundary that we're looking for in that kind of example. So we're trying to find the best boundary that would describe the general case. However, if we keep using the same data to train a neural network over and over again, we can arrive at something that looks like the right image, where the boundary becomes too specific and doesn't fit the general case. And as a result, we're going to lose accuracy for overall cases. So in order to prevent this, we are also introduce a validation data set, which we'll use to kind of compare our results and see that our neural network is not becoming too specific for the training data.
The central question that we aim to at least begin to answer with our research is essentially how the structure of the neural network affects how fast and how efficiently it trains. So in this graph, we have a plot of root mean squared error versus time. Root mean squared error is essentially just a measure of how good the neural network is, where lower is better, and time is just the amount of time it's been training. Now, this neural network is being trained on a training set, which means that it's being shown only examples from this one set of data, which is represented by the red line. The red line is the performance of the neural net on that specific training set. But after each training iteration, it's also tested against a validation set, which is a set of data that is from the same general set as the training set, but it is data that the neural network has not yet seen. So here we see that it is getting better at identifying the training set, whereas at a certain point, the validation set is now being excluded from the knowledge of the neural network. So we are looking to identify how quickly neural networks get to this point, and how good they are by the time they get to this point.
Okay, so now I'll talk a bit about how we generate each set of neural nets in general. We have a set of experiments for which we generate a mock data set, and I'll go into how this is done in the next slide. And once we have the mock data set, we basically generate a set of neural net structures, which are defined by a few parameters. These will go on to create a neural net, and for each experiment, we end up having 1,554 neural nets, all of which are tested against that same mock data set. The fixed parts of those structures, basically what's common between them, are the input layer, which is the same thing mentioned at the beginning. It just starts with two nodes representing the x and y coordinates of a point being fed in for classification. And then the output layer consists of one node, which basically represents the classification output. This is just stored as a binary value, 0 if it was classified incorrectly, and 1 if it's classified correctly. Then what's varying among the structures and what causes us to have those thousands of neural nets is that we vary the number of hidden layers and the number of nodes in each hidden layer. Each neural net can have 1 to 4 hidden layers and 1 to 6 neurons within those hidden layers. That's why we have that range. And just remember that our goal is to see which of these structures work the best so we can minimize that distance between the validation error and the training error that was shown on the previous graph with root mean squared error. So then we generate neural networks from all of these structures and we test them against the generated data set. And the last step is data analysis, which we'll go into a bit later. Okay, so for this presentation, we present two experiments with two different data sets. One has a parabolic boundary, which has like a slight amount of noise. And we also have a control, which is just a simple linear boundary with no noise whatsoever. Noise is basically the bad values in a data set, the same type you'd get in the real world because not all data is perfect. And noise is basically what causes the overfitting that Collin mentioned earlier. And the reason for this is simply because noise provides the opportunity for the neural net to fit into every nook and cranny created by the more jagged boundary, which we see in the parabola. And sigma and peak are just two variables. They're mentioned on the top of the graph, and they just let us control the amount and the spread of the noise around the boundary. And we're interested in seeing the effects of more noise on different structures. We'll touch on the data analysis and stuff a bit later. Now that we're starting to look at the collected data, we eventually generated thousands and thousands of rows of data. We tracked different measures of overfitting, accuracy, number of weights in a structure, and more, all at each epoch of or training iteration of each of the 1,554 neural nets. So we were trying to find interesting trends from this experiment and trying to parse through all of that data. So we graphed a bunch of things against each other, and one of the things we graphed was the total number of weights, which is the same as the total number of connections in the neural net in a structure versus the final accuracy of the structure. And the final accuracy is just how well the neural net performs at the very last training iteration. And the x-axis, being the weights on these graphs, doesn't really show us much, but the graph itself does reveal this sort of grouping of the structures. We have like 3 different groups. The one at the bottom of the parabolic graph on the left, which stops at 75% accuracy, is of particular interest as it consists of these underperforming structures. The top 2 groups perform fairly well, 85% accuracy and above, and 75% may seem kind of high, but given that the data set we pass in isn't that complicated, it's low and bad in this context. And then we see the same kind of problem with the linear experiment. Okay, so we took a look at these underperforming groups in the parabola in particular. Each index in this array, is shown as a hidden layer, and the number is the number of nodes in the hidden layer. So these are just structures. And we see a lot of hidden layers here with just one node. Those are all highlighted in red. And this could be like at the start of the neural net structure, so like the first hidden layer, or with the middle layers. And we observe that in many of these structures, everything in blue in particular is an instance where we go from a hidden layer with a high number of nodes immediately to a hidden layer with one node. And the effect of this is basically crushing a multi-dimensional array of valuable data, everything that the neural net has learned about training so far, into one point or one value. And this is really bad when the drastic switch occurs early on in the training process. And we know that these types of structures produce bad results. And this is something just to note for future research in structure. And also in our own future structure generation experiments. Like in the future, we're going to throw these types of structures out entirely and maybe even start the layer size at 2 instead of 1 for an easier fix there.
So here we have two graphs which basically relate the structure complexity measured in nodes or neurons and overfitting. And just to reiterate, overfitting is calculated by the difference in the training accuracy of the neural network and the validation accuracy of the neural network. So basically how much better the neural network is on the training data than it is on the validation data. On the right is the results from our linear data set. And on the far right of the screen, you can see a color bar, which basically indicates the accuracy of a certain network. The lighter the color, generally the better. So we can see in the linear data set, most of the structures performed extremely strongly, which is expected considering how simple the data set was. And also, as you'll notice by the values on the y-axis, which is overfitting, there was basically no overfitting because there was no noise in this data set. And the neural network did not have the opportunity to overanalyze this noise and overfit to the data set. There are a few exceptions to the high accuracies, which are the black points on the graph, which are basically caused by reasons that were explained in the previous slide. On the left, we have the results from the parabolic data set, in which there are a few interesting trends. Firstly, starting at around 13 nodes, we start to see significant overfitting, which basically indicates that the structure is becoming too complex for the data set that it's trying to analyze, and then that it's ending up over-analyzing the noise within the data set. This means that it will become more specific to too specific to the training data set, and will therefore become less accurate when tested on the validation set. And we can see this poor accuracy reflected in their values. You can see the dark purple indicating around an 80 to 85% accuracy rate, which isn't great compared to the stronger structures. The other interesting trend in this graph is that we can see all of the strongest structures, indicated by that light yellow color, line up along the central band in the middle of the graph at around 0.005 overfitting measure. And this was originally somewhat surprising to us because we would have expected the strongest structures to be closer to 0 overfitting, which would indicate that the structure did not overspecify itself to the training data. However, we believe that the slight overfitting might actually be beneficial because a lack of overfitting might indicate a lack of training, and we would always expect the structures to perform at least slightly better on the training data set than the validation data set.